So this is video 2 in the action potential lesson. We're going to start off by describing how the sodium channel and the potassium channel works. So first of all, as I mentioned in the first video, you should recognize that the sodium and potassium channels, there's a huge variety that act very similarly. Unless otherwise specified, we will consider these channels in nerve and skeletal muscle to be the same channels. But of course, they're generated by different genes, and you should know that. But they act very similarly in both tissues. So we're going to call them the sodium channel, the potassium channel. In fact, it's a delayed rectifier potassium channel. Okay? All right. So first of all, you'll note the sodium channel here. We have an activation gate and an inactivation gate. Both gates must be open for this channel to conduct sodium. Okay? If either of these is closed, sodium doesn't get through the channel. All right? If they're both open, then sodium will cross and flow according to the gradient, the electrochemical gradient. And you will note that at rest, about minus 90 in a muscle cell and about minus 70 in a nerve cell, all of the inactivation gates are generally open and the activation gates are generally closed. So a little explanation here. On the y-axis here, we have probability that the gate is open. So that means that if my probability for the activation gate is 0.6, that means if I have 100 channels, on average 60 will be open, 40 will be closed. Okay? So it's nothing more than a probability. It's on average. If you take the membrane, you put it at that voltage, you hold it there, and you look at the state of the activation gate, let's say at minus 30 millivolts, then 60 out of every 100 will have an open activation gate, 40 out of every 100 will have a closed activation gate. The same thing with the inactivation gate. So if I'm at minus 90, pretty much all my activation gates are closed. I'm way down here, okay? And if I'm at minus 90 here, pretty much all my inactivation gates are open, okay? So that's generally the state of these gates at rest in a normal cell, okay? That's what we mean by that. So I just said that. This is the probability of gate opening, and you will note that it is a function of membrane voltage. That's what's on the x-axis here. And for the activation gate, the higher the voltage goes, the more likely it is to open. For the inactivation gate, the higher the voltage goes, the more likely it is to close. And you will also note that the higher the voltage goes, the faster these gates open, and the higher the voltage goes, the faster the inactivation gates close. So there is a speed factor as well in here. That is not accounted for in these graphs because all we have is probability of opening, but you should note that the rate at which they open does increase as the voltage goes up as well, okay? And finally, the probability of channel opening is the probability that any channel will be open at a given time and voltage, which means the probability that you will find both of these gates open in the case of the sodium channel, okay? So let's talk a little bit. This is a statement I just made. The probability that both gates are open is the product of the values on the curves here, okay? So if I just take the membrane and I just artificially put the voltage at a given spot and hold it there for a long period of time, these are the curves that are generated. So let's say that I'm at 40, 30, minus 20. So about 70% of my activation gates are open, but note that basically my inactivation gates are all closed, all right? So the probability that that channel is open at minus 20 is basically 0.7 times 0, it's going to be basically 0, right? So the question is, if that's the case, you guys know the action potential shoots up. I'm passing minus 20 here, and sodium channels are opening. They're still opening as I go up in voltage here. So the question is, how can this possibly happen when you look at these two graphs and you go, well, this is 0.7 and this is 0. 0.7 times 0 is 0. Shouldn't it be closed? Well, it's obviously not closed. I've generated an open here. I've generated an action potential here, and the sodium channels are still opening as the voltage goes up. So the question is, how does this work? And the answer is that you have to account for time. Okay? The inactivation gate, as I mentioned in the first video, is slower than the activation gate. So if I go to minus 20 and I hold it there, eventually this is the state that you'll be in. Eventually 70% of the activation gates will be open and 0% of the inactivation gates will be open. But because there's a delay here where it takes a while for these gates to get to this 0 state, during that delay, during that period between these activation gates open, like the dinner bell rang, like I stand up when the dinner bell rang, and the time between that and the time between and when these lazy inactivation gates eventually decide to close, that's the period during which sodium flows. And so you get a sodium current, you get an action potential, and it's a competition between the rate at which this opens, which is very fast, and the rate at which this closes, which is pretty slow, relatively, okay? And that's the reason why you get this. And that's important to note. In terms of the potassium channels, again, these are basically delayed rectifier channels. And there's only one gate. It is an activation gate, and it opens as the voltage goes up, okay? But you'll notice that the activation gate on the potassium channel is slower than the activation gate on the sodium channel, and really slower than the inactivation gate on the sodium channel. It's probably comparable. So these are pretty slow channels relative to the rate at which that activation gate in the sodium channel opens. But these open as the voltage goes up, just slower. So how is an action potential generated? We have a membrane depolarization caused by something that we'll get to in the synapses lecture, okay? And the sodium activation gates begin to open due to that depolarization. So if I quickly depolarize the membrane to minus 50, then I'll get maybe 10% of my channels that will suddenly flip open. My activation gates in 10% of the channels will suddenly flip open, okay? And that will allow sodium to flow because these channels at rest have mostly open inactivation gates. Now those inactivation gates are going to begin to close, but they close relatively slowly. So if this depolarization is pretty quick, 10% of my activation gates flip open, and my lazy inactivation gates will start to close, but it's going to take them a while. And in that period in between, you have sodium that flows. Okay, so we get an inward sodium current. That is positive charge coming into the cell. Okay, this is the equation which tells you what that current is. This membrane voltage minus the equilibrium potential for sodium, which is a pretty big number, times the conductance for sodium, which is proportional to how many channels you flipped open here. Okay, so that generates a current, INA. All right, the more channels you flip open, the bigger INA. Okay, so the bigger your depolarization here, if it's quick, the bigger this term, meaning the more open channels you have, and so the bigger this term, which is the sodium current. Okay, so sodium current begins to flow, and as the sodium flows in, you're bringing positive charge into the cell. That raises the membrane voltage even more, and so now you've flipped open more activation gates, okay? And when you flip open more activation gates, you bring even more sodium in, you raise the voltage even more activation gates open, okay? So it's a positive feedback system where the more sodium you bring in, the more depolarization you get. The more depolarization, the The more open sodium channels, the more sodium flows in and the more depolarization you get, okay? So that positive feedback causes your upstroke and your action potential like so, up, okay? The voltage is driven toward the Nernst potential for sodium, which is maybe plus 60 or plus 70. So the more sodium you bring in, the more you increase the permeability to sodium by opening sodium channels, the more the voltage migrates toward plus 70. You're bringing positive charge into the cell, okay? And sodium channels begin to inactivate as our voltage goes up. Inactivation gates, slow, lazy, but eventually they get around to doing what they're supposed to do, which is close. And as that happens, your sodium channels inactivate and the sodium stops flowing through the channels, okay? So that happens as you start to near this peak here, okay? And the sodium channel begins to get cut, sodium current begins to get cut off as your inactivation gates close. You also are beginning to have significant opening of potassium channels because they open as the voltage goes up. Potassium will drive you down toward its equilibrium potential, which is about minus 90, or we said minus 95 in some earlier videos. It's about that area, okay? And so the more of these that open, the more your voltage is going to tend to go down toward minus 95. So you're decreasing the permeability to sodium and decreasing the tendency to migrate up toward plus 70. At the same time, you're increasing the permeability to potassium and increasing the tendency to go toward minus 89. Positive charge leaving the cell during this downstroke, potassium going out, flowing from high concentration to low concentration, and that brings your inside your membrane to, it makes it more negative, and you head toward rest, okay? So there's our potassium channels, they're opening, they're bringing us down toward EK, the Nernst potential for potassium. And then finally, in the nerve, we get what's called a hyperpolarizing after potential. That is, the voltage actually sinks below rest, okay? And this is caused because as your voltage comes back down and you get into this, minus 70 area here, the channels are closing again. They basically close themselves. As they allow potassium to go out, the voltage drops, and as the voltage drops, the potassium channels close. But just like the opening of the potassium channels, the closure is pretty slow too. So when you get down to the resting potential, you still have a significant number of potassium channels that are open. They're trying to close, the voltage is down, but they're just pretty slow about it. So you go beyond the resting potential because you have a relatively high permeability to potassium. So you get even closer to this minus 90 equilibrium potential. And then as those potassium channels gradually catch up, and as they gradually close and get back to where they're supposed to be, your membrane voltage migrates back up to where it ought to be at rest because your permeability to potassium is gradually decreasing and you're gradually migrating away from minus 90 till you come to your resting potential again. So that's why you get a hyperpolarizing after potential in nerve, okay? And then you get a depolarizing after potential in skeletal muscle. This is due to a different reason. When potassium exits skeletal muscle membranes, it exits into the T-tubule. Now for our purposes, the T-tubule is basically extracellular space. It's just this tube that dips down into the cell, but it's open to the extracellular space. So the potassium's going out into the T-tubule. But the problem is that if it's going out into the T-tubule and the T-tubule is deep within this, the myofibril, it takes a while for that potassium to diffuse out of the T-tubule and into the extracellular space. So during that time, you have an excess of potassium on the outside of the cell in the T-tubule. So if we look at our Nernst equation, the higher the extracellular ion concentration, the higher the Nernst potential. So the Nernst potential, instead of being minus 89, will probably be higher than that. So instead of bringing your voltage down with your open potassium channels and migrating toward minus 89, the potassium accumulation in the T-tubule is causing you to migrate toward a less negative number, and so you stop short. And then as the potassium gradually diffuses out of the T-tubule, the nursed voltage, the equilibrium voltage, gradually migrates back down to where it belongs, to about -89, and your membrane voltage migrates down along with it, okay? Because most of what you have is rest, is open potassium channels, and open potassium channels make you migrate toward the equilibrium potential, okay? It's just that the equilibrium potential is probably higher than it ought to be here because of the accumulation of potassium, and then as the potassium gradually gets back down to where it belongs in the T-tubule, those open potassium channels will be pulling you down toward a more negative number, and so your resting potential will go down with it. So that's why you get a depolarizing after potential in skeletal muscle, because of the presence of these T-tubules. Kind of interesting. We have absolute and relative refractory periods. The absolute refractory period is when you're actually depolarized, because your sodium channels are still inactivated here, and probably for a little while, pretty much completely activated. During the entire time that you're depolarized here, your inactivation gates are closing, and you can't depolarize the membrane and get those inactivated channels to open again, because that gate's closed. You have to wait for those inactivated channels to recover, and then you can get a depolarization. So the absolute refractory period is during this depolarization. There's no way you can get an active potential. There are just too many inactivated sodium channels. And then as they gradually recover, during this hyperpolarizing after potential and during the depolarizing after potential, you get to the point where you can generate an action potential, but it's not a real great action potential. It's harder to generate, so we call that the relative refractory period, where you can kind of get one, but it's really hard. And not only are the sodium channels recovering, in this phase you've actually got potassium channels in the hyperpolarizing after potential. Too many of them are still open because they haven't closed yet. That makes it harder to depolarize the membrane. In this case, until the membrane gets really down closer to rest, some of those inactivation gates are still open. So again, even during this phase, it's harder to generate an action potential in the skeletal muscle. So those are our absolute refractory periods. Okay? Let's cut it off there, and we'll move on to our next video with a description of the threshold, how that varies, and what causes the conduction, the velocity of conduction to vary as well. All right?